Okay, so this might be my favorite theorem in all of group theory, in all of abstract algebra. It says that if you have two normal subgroups with trivial intersection, then the elements of those subgroups commute with each other. And it's just amazing because there's so little information here, and to conclude that elements commute, it's kind of surprising. And the proof is just brilliant. Okay, so suppose, like in the statement, that H and J are normal and H and J have trivial intersection. The key is to consider this element G, which is a commutator between H and J. And the key is that because if G is the identity, if we are able to prove that G is the identity, then we can send this H inverse and J inverse to the other side of the equation and conclude that HJ equals JH, so they commute. So how are we going to prove that G is the identity? The key is to write G in two different ways. So first, if I consider this little j here is in J, and if I conjugate it, since capital J is normal, I'm conjugated by an element of G, this whole thing is in J, and if I multiply by something in J, then I get something in J. So this whole thing is in J, and therefore G is in J. On the other hand, if I do the same thing with this element H inverse, that's in H, if I conjugate it, this element has to be in H because H, capital H, is normal. So this is in H, and since this is in H and this is in H, the product is in H, and therefore G is in H also. Thus, G is in the intersection, is both in H and J, but that intersection is trivial. Therefore, G has to be the identity, and we're done.